Okay, great. Thanks very much. Thanks the organizers for having me here. It seems like an interesting meeting. I'm going to talk about some experiments that we've been doing in the last roughly year or so. I'll focus on one particular experiment, but we've been, over the last couple of years, been working on few-layer graphene. I'll try to kind of convey to you in a broader sense what's interesting, and then I'll spend most of my time talking about these measurements in a multi-band system, which is this tri-layer graphene, some interesting measurements of Berry's phase. Okay, so the gory details are in these papers. I'll try to convey the essence of this, and I should point out that one of my students who contributed to this work is presenting a poster. So let me make a plug for him. If you have time, please go and check out his poster, and you'll get to know more things than what I'll tell you. I am grateful for the financial support that makes our research possible. So ICTS and TIFR, of course, both are funded by Department of Atomic Energy. So we gratefully acknowledge, and we also have some funding from Department of Science and Technology of India, which makes this work possible. So before I get started, let me just briefly acknowledge the great collaborators that I have, which make this work possible. So first of all, the student, Biswajit, is the student who did most of his work. He's just finishing up his PhD. Pratap is here, and he will be at the poster. Then two other people who have collaborated a lot with understanding this system is Rajdeep Sen Sarma, who's a theorist at TIFR, and his student Abhishek. Rajdeep and his student, and for the part that I'll spend most of the time talking about, we've collaborated with Justin Song and is at NTU, and his postdoc Lee Kun Shi, and we've learned quite a bit about things we didn't really know much about. Okay, so let me just quickly show a brief outline just so that the overall direction in which sort of I'm going to proceed throughout this talk is clear. So I'm going to start off by telling you why few layers of graphene are interesting, since this is the first sort of graphene-related quantum Hall or quantum transport talk. I'll spend a little bit of time trying to give you a big picture of why this is an interesting system and kind of deserves some attention. Then I'll talk about the particular system that we are interested in, which is 3 layers of graphene, tri-layer ABA graphene, and I'll give you some examples of how symmetry can be broken using a simple knob, which is an electric field, and that can lead to some interesting physics. And then I'll go into how we measure the Berry's phase, which is using quantum oscillations of different bands. Okay, and then the take-home message from our work, which we're kind of interested and excited about, is that if you have multi-band system, there is some way to access, because of a filling constraint, because you have an overall same density through bands, you can get some sense of the Berry phase of another band by measuring quantum oscillations of a completely different band. So that's the take-home message. Okay, and I'll kind of slowly give you all the ingredients that are needed to understand the physics that I'll describe. So just one slide about graphene, which everybody here certainly knows a lot about, but for the sake of completeness, so this is a simple sort of scaffolding or the lattice structure where there are these two inequivalent sites, A and B, and the fact that these two sites are inequivalent, but in case of graphene occupied by the same chemical species, leads to interesting physics that is kind of hallmark of a lot of interesting properties in graphene. This symmetry can also be broken, and you'll see some versions of it in the example that I gave later during the talk, using external knobs like an electric field. So you essentially have a way to lift this symmetry in certain different lattices. So this crystal structure is known, and we know what the dispersion of this band near the Fermi energy looks like. And we also have very good understanding over the last several years about the structure of the Hamiltonian at two inequivalent points in the K space, which is the nearest neighbor points in the K space where the conduction and the valence band kind of touch each other. So a lot of exciting work has been done in graphene, and it has led to interesting physics, but one of the things that has been a little bit tricky is monolayer graphene itself does not have very easy ways to see effect of electronic interaction. So most of the physics that has dominated a lot of the research in this field is mostly non-interacting physics. Interactions are important, but at some extreme conditions, very large magnetic fields. But as I will show you, an opportunity presents itself in the form of few layer graphene, where some of these interaction effects can be kind of can be enhanced to your advantage in less demanding circumstances. So that's sort of the big picture of why few layers of graphene are interesting. There are several examples in the recent past that have really made dramatic sort of demonstration of why moving from graphene, few layers of graphene is interesting. So, one of the properties of graphene is its unique band structure, but as you move to a few layer graphene, the energy momentum relationship is not linear. In fact, in some general sense, if you go in a particular kind of stacking, the dispersion is related to the number of p to the power number of layers. So as you go to increasing the number of layers, it becomes flatter and flatter. Okay, so if one wants to look at physics of interactions, that is nice because the bands are becoming flatter and you have a relatively more important contribution of electronic interactions. Of course, if you have some certain symmetries, this is the band structure of the system that I'll talk about. You can have a Dirac band which is gapped. So it's not a massless Dirac fermion band, but it has a small mass associated with it, and it exists with a kind of a massive Dirac band as well, or you can think of it as a parabolic band. Again, here interactions can be seen in dramatic fashion as well. So, the three main reasons, interactions, the fact that you have an avenue to tune some symmetries by applying different voltages or electric fields is kind of sort of the main point why these systems are interesting. And of course, there is an increasing interest in, for particularly people here at this conference, there are now growing efforts, certainly already demonstrations in bilayer graphene, interesting fractional quantum Hall physics, and there are some interesting proposals for studying this physics even in sort of more number of layers as well. So interactions become important I won't really have time to talk about it, but you can see very nice quantum Hall ferromagnetism at extremely low magnetic fields in systems like these trilayer graphene, which is quite distinct from monolayer graphene, where you really need to go to extremely large magnetic fields to see the effect of electronic interactions. So, there's in the last roughly about 15 or 16 months, there has been a kind of a dramatic new entrant in the sort of graphene quantum transport world, which is this twisted graphene, which is two layers of graphene stacked on top of each other. And they're sort of the biggest advertisement for sort of the key role of controlling symmetry, which is by controlling the angle and electric field, which is perpendicular to the two layers. You can realize very complex states of matter, correlated insulators, and right next to correlated insulators, superconducting states. So, in terms of what graphene didn't really have, in adequate measure, is this interactions really come out to the fore when you look at few layers of graphene. This is one really classic example. So, in a simple cases of symmetry having kind of important consequence on the electronic properties is the same structure, which is graphene and boron nitride, or cousins of boron nitride or graphene, which are these dichalcogenides. They're effectively the same basic structure, which is the honeycomb lattice, but lifting this inversion symmetry by either having some different chemical species. So for the case of graphene, you have this simple Dirac Hamiltonian, but the moment you lift this inversion symmetry, for the case of boron nitride, you basically have one boron and one nitrogen, and as a pair, they're isoelectronic with graphene kind of dimer, but it is a very nice insulator with a band gap of about 6 to 7 electron volts. So this symmetry playing an important role, and the fact that all you need to do to break that symmetry is that on-site potential of these two in your lattice structure are different, is kind of important. And I'll show you one more example in the next few slides where this is brought out. So symmetry is kind of a very interesting knob in these systems. In general physics has lots of examples, but these systems are particularly amenable to a lot of interesting manipulation. So a classic example of this is a kind of tunable symmetry breaking. Is a bit old, but it's simple bilayer graphene, 2 layers of graphene stacked on top of each other. And if you look at the spectrum of just 2 layers of graphene, and this allows for hopping between different sites, is kind of gapless. It's metal-like 2 bands. But the moment you apply a perpendicular electric field, you actually break the symmetry of the system, and you open up a band gap. And this band gap is tunable with the perpendicular electric field. It scales up to about 200 MeV or so with large electric fields. So you can, there are not many examples of being able to tune band gap so nicely. And this is also, you can understand very simply, this is the crystal structure, and this is sort of the simplest depiction of this lattice. The moment you apply a perpendicular electric field, you will break the inversion symmetry across these 2 lattices, because this guy will have a slightly higher potential energy than this guy, and that symmetry is no longer available for you to play with. So this consequence of kind of ability to tune sort of in situ these Hamiltonian in some way is kind of really nice. And in the last few months, there have been really new and exciting proposals for looking at few layers of graphene where the bands have interesting topological properties. So for example, this is somewhat experimental realizations have been, some reports have been published. Is a version of graphene, trilayer graphene, ABC, and I'll kind of explain ABC in case you don't understand the sort of the technical nomenclature. You can basically have bands which have different Chern numbers, and using combinations of electric field and your ability to tune the Fermi energy in the system, you can go to different topological states inside the same device. Okay, so this is really exciting, and the experimental work is kind of just sort of starting in demonstrating some of these ideas. So, so overall, this is sort of my pitch for why this kind of systems are interesting for not just quantum transport, but a lot of interesting topological physics as well. So this is sort of where I'm on. Outlines I've given you a broad sort of pitch for why this kind of a system is interesting. So let me now jump into a little bit more detail about our experimental system, what makes it interesting for us and for detailed studies. So this is ABA stacked trilayer graphene. There are 3 layers of graphene. So in the naive world, if you don't have the coupling between them, which is hopping between different sites, these are just 3 copies of graphene, okay? But the fact that there is hopping of an electron between different sites, these parameters, which are hopping rates, gamma 4 and gamma 5, these are small numbers, but these are actually very important to actually describe the system completely. And we, in our measurements that I will really not have time today to talk about, using kind of detailed quantum Hall measurements, you can precisely measure these numbers, which in the past have never been sort of measured accurately and a bound put on them. Okay.
This gamma 5 doesn't
Yeah. Yeah. But its contribution can be measured. If you write down I'll show you in the next few slides, won't have too much time to go into the gory detail, but you can actually measure in the Landau level evolution the influence of these parameters so that you can pin them down. And even in the topological bands that I told you, if you look at simple toy models, inclusion of these things breaks some important symmetries, like electron-hole symmetry in the simple toy models for, say, twisted graphene. These parameters become important. Okay, so what you get is you get two bands. So first of all, you would, if it's just three copies of graphene, you'll get some bands. But one of pair has a gap here, so it doesn't really come into the picture as far as the electron transport goes. So you end up getting a Dirac band and a parabolic band or a bilayer graphene-like band. Okay, I'll show you the Hamiltonian in the next few slides. So in the absence of a perpendicular electric field like this, these two bands don't talk to each other. They don't hybridize at the points where we cross. And this system has a mirror symmetry. So until that mirror symmetry is preserved, you're good with this simplified picture. But the moment you break this mirror symmetry, some interesting physics starts to happen. Okay, so in a kind of a nice, cool-looking picture, what you have is a sort of conical band, and around it is a trigonally warped band around it. Okay. And there is no electron-hole symmetry in this system, even in the absence of any electric field or any external potential. So the symmetry is already broken. And there is a small gap, and more about that in the next few slides. Okay. So in the absence of an electric field, these bands look like this. But when you turn on the electric field, which is parametrized by this parameter delta 1, which is just the potential of the outermost layers, this is upper one will be plus 20, lower one minus 20. Bands start to hybridize. And there's a simple way to, the effective way to see this, which is the effective Hamiltonian of the system. It is a 6 by 6 and Hamiltonian, which has two blocks. One is this Dirac Hamiltonian with a small mass term. This is the bilayer-like term. And these off-diagonal elements are the terms which are, delta 1 is directly the perpendicular electric field. So in the absence of an electric field, you have a very nice block diagonal system where, again, there's no hybridization. But the moment you turn on electric fields, the band will hybridize. But this is a topologically non-trivial band in the middle, the Dirac band. And that's sort of the focus of the experiments that I will talk about. You can see, even in this system, which is a little bit more complicated, that as you apply a perpendicular electric field, you can essentially increase the mass of the Dirac fermions that are there in this band, okay, which is kind of nice and interesting for some experiments. So I'm an experimentalist, this is sort of what our device looks like, which is a sandwich between layers of boron nitride, which is an insulator, which is a very good insulator, and that's one of the reasons why we use it. And once you make this device, you can have electrodes which are for measuring quantum Hall measurements in plane connected, and then gates which are top gate voltage and bottom gate voltage, which will allow you independent control of density and electric field. And so these devices can have very high mobility, and our devices indeed have high mobility, which allows exploration of some of the physics. I'll try to point out. The mean free path is very large, comparable to the device dimension, so these devices are kind of ballistic. And this is sort of the cartoonish geometry. There are 3 layers, and the electric field will basically only change the potential of the 2 outermost layers relative to each other. And then there's another parameter, delta 2, which, again, I don't have time to talk about, but the essence is that there is an inbuilt variation in the electric field. It's not linear throughout, even though it's only 3-layer system, it's non-uniform. And we have kind of benchmarked the parameter delta 2 is essential to kind of completely see the features that we experimentally observe. Okay, so once you have this, when we do transport measurements, we will basically do experiments at low temperatures and apply perpendicular magnetic field and other voltages like the 2 gate voltages. But one way to kind of imagine is that you basically see the quantization and sort of Landau levels forming in the 2 bands, and they behave quite differently because one is sort of graphene-like Dirac band, and another is kind of the usual parabolic or bilayer-like Hamiltonian. As you apply a magnetic field, nevertheless, in both the systems, the Landau levels will move apart, which is sort of what one sees. Peculiar thing you will see is that there are these 2 pink dots at the edges of the Dirac band. These are sort of split versions of the n equals 0 Landau level in graphene. One half goes to the upper part of this Landau level band, and another one, and they don't disperse with magnetic field. Okay, so these are, in some sense, very close, similar to graphene. And so you can calculate the Landau level spectrum, and what you see is you get Landau levels which are green, marked as green. They arise from these bilayer-like bands. So they disperse much like the quantum Hall that you would expect, which is proportional to B. And the pink ones are the ones which arise from the Dirac band, and they disperse as square root of B. Okay? And what you will see here is that this band is split across the 2 edges of the gap Dirac band. This will become important in the talk as I go on. Can you hear me? Okay. Maybe I'll continue. So, as we already kind of know, the gaps in this Landau level spectrum of Monolayer-like band weird. Okay. Okay. Thanks. The energy level spacing on the bands, for example, this gap between n equals 0 and n equals 1 on the electron is much larger than the spacing at the same magnetic field. It's much dramatically seen in this simultaneous evolution of the bands. And this band, of course, does not disperse with magnetic field. So you can actually start to, have this system, and now you kind of, it's available for exploration. What you will see is a crossing points of these 2 Landau levels whenever they become degenerate. And you will see crossing points here, you will see crossing points here. I should point out that this axis is energy, but in experiments, this axis is not energy, but is density. It's connected, but it's not proportional to it because you have to use the density of states to go back and forth. This is thus far still consistent with what one knows about quantum Hall in monolayer and bilayer-like systems. Now, what we're going to do is sort of look at the sort of extremely low magnetic field evolution of these crossing points as a function of a perpendicular electric field as one breaks the symmetry of the system, which is the mirror symmetry. So what do we experimentally measure is we measure something. This is experimentally measured raw data, which is plotted in a color scale. So most people are familiar, but let me just take a moment to explain. The color indicates the magnitude of the conductance, red being large and blue being low. And what we have is 2 knobs, which is density and electric field. So normally I have 2 gates, top gate and bottom gate. You can do a kind of a rotation with device parameters involving capacitance, and you can independently go to a parameter space which is density and electric field. Okay, and you can take excursions which keep the density of the electron density to be the same and move the electric field, increase it or decrease it. And it's just a simple linear rotation, remapping. So if you have only 1 gate in your device, you cannot independently control density and electric field. So you need 2 gates to be able to do this kind of rotation. You have a question? This is GXX. So white here is in the middle. So this is a kind of a weird scale. White color is intermediate between red and blue. you will see it a little bit clearly. So this magnetic field is a kind of a teeny tiny magnetic field. Okay, at this field, you will typically not see Landau levels, but if you look carefully here, because the mobility of this system is large, you can see these tiny fringes here. These are actually sort of things that will become Landau levels. What you see, these bright lines are actually not Landau levels, but they are crossing points of the Landau levels spectrum of the monolayer-like band and the bilayer-like band. When they overlap, you get additional density of states. That's why their sort of magnitude is larger. So these are not Landau levels, but these are crossing points of the Landau levels of the two systems. Okay, so this field is very, very low. Typically, if the mobility is modest, you will not be able to see some of these details. So what one can actually understand this spectrum by comparing it with sort of calculations, simple calculations. But the thing that stands out at this crossing points, that is the crossing point between the two Dirac bands. And so these are, so if one tracks this crossing point with electric field, you'll see that they move apart. This is one half of the n equals 0 Landau. This is another half of the n equals 0 Landau level, which is basically increasing as you increase the electric field, keeping the magnetic field constant. There's a reason why we do these experiments at low magnetic fields. We, of course, have done lots of experiments when the Landau levels are fully resolved as well, but it allows us to see something in the parameter space of the electric field much more clearly, the consequence of this symmetry breaking, the mirror symmetry breaking. And you can extract out the gap in this system, which is a very small gap of about 1 milli-electron volt by doing the quantum Hall measurements and measurements like this. But it's nevertheless a gap which is kind of useful because, as you'll see in the next set of experiments, that as we can tune the Fermi energy through the band gap of this Dirac band, and which is interesting when we look at the quantum transport. So what has happened is here in this sort of this particular data that I showed you is that similar to bilayer graphene, I have a perpendicular electric field which breaks the mirror symmetry, but it also, in this sort of complex-looking Hamiltonian, effectively changes the mass of the Dirac fermions that which are already gapped. It'll enhance that gap even further for experiments that you can actually look at in detail at higher magnetic fields. So this kind of hopefully sets up sort of the experimental that I'll kind of focus on in the next 20 minutes or so, that we have a system which we can understand different components of the system very well, and we can now start to look at quantum oscillations of the different bands and try to extract some information about the Berry's phase associated with the different bands in this multi-band system. Okay, so let me get started. So of course, Berry's phase itself is sort of now used in different contexts, but some of these early ideas of Berry's phase were actually proposed by Pancharatnam in the context of optics, and it was much later that was generalized by Berry in a much broader way that it's actually known as Berry's phase. So it's a geometric phase. So in a kind of parameter space, if you kind of do some cyclic paths, you can actually pick up a phase which actually can be measured. So in transport systems, the way you measure the Berry's phase is that you apply some voltage and the electron is kind of drifting around in your system, which is a kind of a trajectory in real space. But while that's happening, it's also actually moving around in K space and making loops, closed loops on itself. And as it moves around in K space, it will pick up the topology of the so the Berry's phase associated with the topology of the band, and it can be either trivial phase or a non-trivial phase depending on the band property. Okay, so and that's really been used a lot. So for example, Berry's phase in bilayer-like or systems or quadratic dispersion, the Berry's phase is basically 2 pi. And in systems like graphene, monolayer graphene with a Dirac Hamiltonian, you have a Berry's phase which is pi. And this is sort of the same non-trivial topological phase that will be there in topological insulators on the states at the surface as well. Okay, so we will basically try to do some physics related to quantum oscillations in this system, which I already kind of introduced. And so I showed you the consequence of large magnetic fields where the large Landau levels are formed. But there's another interesting consequence which connects the Berry's phase, which is when you quantize, semi-classically quantize these closed loops in the K-space, this quantization brings in the Berry's phase because this is related to the Fermi surface area, but which is n is an integer, but along with comes a phase. Okay, and this phase is related to this quantity, which is Berry's phase, and it provides direct access to measure these properties of this the Berry's phase associated with that band by measuring what are called quantum oscillations. And what the way we want experimentally measures, there are many ways to measure it. Either one measures transport, or you measures either Shubnikov d Haas or d Haas 1 alpha. You will basically be able to pick up this phase in those measurements, and I'll kind of briefly outline how this happens.
Okay.
Yeah.
There's no assumption that this the curvature is concentrated at a point or anything like that.
No. So far, nothing peculiar is there. These are all general ideas. I illustrate with this example of the system that I'm going to talk about, but I mean, all of this is well accepted in the wider community. So people have used it quite a bit. It's a kind of standard tool for measuring multiple Fermi surfaces in complex systems, multiband systems. But this was also demonstrated for the case of monolayer graphene. What you do is you basically measure the magnetoresistance and you kind of remove a kind of smooth background, and you'll see these oscillations in the resistance. And these oscillations in the resistance can be sort of thought of periodic oscillations, where this oscillation in the space of 1 over b is related, Bf, which is related to the Fermi surface area, and this parameter beta allows you to extract the Berry's phase. Okay, so if you track the minima or maxima of the oscillations, you have to be a little bit careful, otherwise you can be phase shifted by a factor by a pi. You have to be very careful about this. You track those minimas and you plot them in a space of 1 over b. This is basically whatever is inside, and you'll get a line. Okay, the slope of the line will give you the information about the Fermi surface area, and the intercept at 1 over b going to 0 limit will give you information about the phase. Okay. And for the case of monolayer graphene, it was demonstrated that the Berry's phase is pi minus pi in the conduction and valence band. This was kind of a sort of smoking gun evidence for the non-trivial topology of the Dirac band. Okay, so one can also try to do this kind of measurement, and it's routinely done in condensed matter systems. You can try to do these in multiband system, and so in this case, we have a trilayer graphene. The peculiar thing is whenever there is a gap in your band, the Berry's phase will actually continuously deviate from its value far away from the gap and go to 0 in the gap, and then heal back up again over some energy scale which depends on the dispersion that you have in your bands. Okay? So in this case, what will happen is that the Berry's phase for the monolayer band will be pi minus pi, but in the gap, it will actually deviate from pi. And that's sort of the focus of our work. Similar things will happen even for the case of bilayer-like band, but we will not access energies which are in this window for this experiment. So for now, one doesn't have to worry about what's happening to the Berry's phase of the trivial band. So in terms of terminology, a green band is topologically trivial band, and red is the topologically non-trivial. Yeah.
In the gap there, mass, very phase of Ganpathy is not localized to a point, it's spread over the
Yeah.
gap. So when you talk about very phase pi, very phase, do you mean integrated over the whole gradient? So
Yeah, so that's right. So there will be actually a hotspot of Berry curvature at that point. So if you plot the Berry curvature, so one way to think about the deviation of the Berry's phase as you go close to the point is actually you'll enclose less of that Berry flux. So it'll start to deviate. But far above, if I go to much larger K values, I will pretty much enclose everything, else I'll still get a robust pi very quickly. That happens.
And how does that manifest in this quantum level?
It doesn't show up in the energy shift of the Landau levels. It's difficult to disentangle that effect of the Berry curvature, if that's what you mean. But what I'm trying to show you in the next few slides is that you can sense the Berry phase associated in the quantum oscillations. If you want to sense the Berry curvature, you have to do some sort of non-local measurement.
Oscillations, by doing this interpolation, you get exactly the phase.
Yeah. Okay, I hope that answers. Okay, all right, so I will restrict. So, as one goes close to this edge where the band is effectively ending, it's hard to do quantum oscillations because there are no states available to see quantum oscillations. So it's a tricky problem. If you just have a single gapped band, it's hard to do. So what the essence of our experiment is that we will use the quantum oscillations of the green band and try to see, as we change the Fermi energy, does anything happen to the quantum oscillations of the green band, which is the topologically trivial band, as we move the Fermi energy through it. When I move the Fermi energy, I don't really have control over the Fermi energy of individual bands, but the total Fermi energy of the system. Okay? And that's what you'll see. So these are sort of Landau level fan diagram, but at low magnetic field. So for doing the Berry phase analysis, you don't want the Landau level, typically the prescription, you don't really want the Landau levels to be fully formed, and you look at relatively low magnetic fields. So what you see is, again, a plot of conductance, longitudinal conductance. We have simultaneous measurements of Hall conductivity, which I won't really talk about much here, but it's there in our papers. So what you see is Landau levels, which fan out as a function of magnetic field. These are the crossing points of the Landau levels of the two monolayer-like band and bilayer-like band. And this is the crossing of the n equals 0 Landau level with the fan of the bilayer-like band. So just to get you comfortable, this is the correspondence. Let me point out, this is gate voltage, this is energy. They're related, but they're not proportional. Okay? So this is the n equals 0 Landau level of the monolayer band, monolayer-like band, gapped, intersecting with a whole bunch of Landau levels which are coming from the bilayer-like band, and these are crossing points of other bands, -1, -2 of the Dirac band with the bands of the bilayer-like band. Okay, so in terms of understanding what's going on, again, these are oscillations. So what are SdH oscillations are basically slices of the data taken in this direction at constant Fermi energy is basically called SdH oscillations. And we will slice data at constant gate voltages. To understand where we are relative to the band in the absence of magnetic field, I'll kind of rotate the picture, and this is where. So if I look at the band, this is the region in the experimental space where the band gap of the Dirac band is there. And what we can see is when you start to measure the quantum oscillations, this is at large densities, you'll see resistance oscillations of two frequencies. And this is not surprising because if I am at large Fermi energies, I have two Fermi surfaces, and we know from basic condensed matter that we will see quantum oscillations of two bands. And the frequency is inversely related to the area. So these more frequent oscillations are due to the bilayer band, and the infrequent ones are due to the monolayer-like band. Okay, so this is just cross-checking with what we already kind of know well. So now what we'll do is we'll measure quantum oscillations of the bilayer-like band. So we'll measure, I already told you that because the density is kind of vanishingly small, you can't really measure the quantum oscillations directly of this monolayer-like band. So you measure the quantum oscillations of this green band, and there's no difficulty for us to identify because we know exactly from experiments and theory which band is which arises from which Landau level arises from which band, monolayer-like or bilayer-like. So if I measure these quantum oscillations, so I measure the quantum oscillation here, then I tune the Fermi energy because my experimental system allows me to tune the Fermi energy. I measure when the Fermi energy is positioned in the gap of the Dirac band, I get this. And when I'm back in the valence band, I get another oscillation. So first thing that kind of strikes you is that the green and the blue oscillations are in phase, that they are, the crests lie on top of each other. Whereas the red is not really in phase, it's a phase shift, exactly pi phase shifted from these two oscillations. So this is kind of perplexing and interesting. Why, because the Berry phase is a extremely band-specific property that whenever electrons are moving, only the electrons which belong to that band feel that Berry's phase. So it's not really outer band does not pick up the Berry flux of the inner band. So what's happening, so just to give you an idea of how we experimentally do it, what you really do is you measure these quantum oscillations and you kind of fit the minimas at different points. So each point is actually a whole data set of slice, gives rise to one point in your measurement. And you look at the intercept of this line, which allows you to extract the phase. So here it's a phase of minus 0.5 pi, this is 0 pi, and this is 0.5 pi. So we can extract out the phase of this bilayer-like band. So as long as you're away from the band gap, you see this kind of all these detailed analysis, you always get a Berry's phase of that band, which is either 0.5 times pi, and whereas if you measure in close to the band edge, you will see that actually it will deviate from that value. And in fact, right in the middle of the gap, that phase that you will pick up goes to 0. This is kind of consistent when you are in the gap of this Dirac band. It's as if it's completely filled band. It does not really participate. So you get the Berry's phase that you expect from the trivial band, which is the 2 pi Berry phase or the 0 Berry phase of the trivial band. Yeah. That's a good point. It's basically a convention that the Berry's phase associated with the valence band and the conduction band. You're absolutely right. Pi and minus pi is not distinguished. Anything that's modulo 2 pi cannot be distinguished. Sorry? Yeah. Yeah, they are. You can see they're in phase. It's mostly so the intercept here. You're absolutely right. It's just a convention in terms of the conduction and valence band, but it's effectively it's modulo 2 pi. So as you go in the gap of this Dirac band, you'll see that the Berry's phase deviates, and when you're perfectly in the middle of the gap, it's as if the monolayer-like Dirac band doesn't exist. You get the Berry's phase that you expect from a topologically trivial band, which is 0. Okay, so when you lock out the Dirac band, you get the Berry's phase that you expect. So what is surprising is that in these two cases, I'm actually picking out a Berry's phase which is not a property of the quadratic bilayer-like band. It should be 0. So it's kind of weird. We spend a lot of time scratching our heads about why this is happening. And so the reason for explanation for this is kind of simple but interesting, and that's sort of what I will. So how does one understand this anomalous phase shift that I have a trivial band which is picking up a non-trivial phase, and so it turns out the essence of that idea of this pickup is the fact that when I have a gate voltage, I don't have a way of populating each of the two bands individually, independently. I control the overall density, the Fermi energy in both the bands simultaneously. So there is a kind of a density-induced constraint that kind of results in this sort of additional phase shift that you see. It's not that the electrons in the bilayer band pick up this Berry phase, it's just that the quantum oscillations will pick up this Berry phase. Okay? So there's a kind of subtle but important distinction. So what happens is when you do this measurement, you measure the oscillations, and we are measuring the quantum oscillations in this regime. For example, if you look at this regime, these are bounded in between the two lambda levels of the monolayer band. On this side, -1 and 0, and I have precisely half of that n equals 0 lambda level is filled. So that the fact that in this region, if I measure the oscillation and there is a constraint of density, what I'm picking out is the important consequence of the fact that there's half of n equals 0 Landau level, which is sort of, some people think, and I kind of agree, is sort of the place where the Berry phase of pi arises from, is filled. So this filling in force constraint gives rise to quantum oscillations. So the most general way in which you would write down these quantum oscillations is quantum oscillations of monolayer band and bilayer band. But if you're looking at oscillations in between monolayer band, there is no oscillation of the monolayer band, so that term is kind of smooth background. And so this is the term that you end up getting. But we are not really measuring oscillations in the space of individual band density, but densities of total. So when you do this kind of readjustment, you'll basically see that there is a phase that will pick up, which reflects the fact that you have filled half of this n equals 0 Landau level. And as you move the Fermi energy and you position the Fermi energy in the gap of the n equals 0 Landau level, you will basically get no more of that phase factor. And then you go to the other side, you will basically get the other sign. But again, everything is modulo 2 pi. So if you measure continuously, this is something, if you try to extract the phase as you go through the band edge, you will see that its pi drops, and this is sort of the band diagram rotated by 90 degrees, which is this bilayer-like band green, and this is the monolayer gap. You will see this phase shift starts from pi, goes to 0, and goes again to minus pi. So the fact that this quantum phase is sort of getting picked up by density constraint is important, and there is a kind of independent cross-check to verify this. So sort of, I forgot to say something, which is, in the region where you see partial phases is a little bit tricky territory because you are trying to measure Berry's phase as a function of the filling of the Landau level, and it's a tricky interpretation, and we are not 100% sure about what it means, but this is sort of one would expect how the Berry's phase would vary. So there are other contributions that might come in, which is sort of fractional filling of the Landau level. But in the limit of when the Landau level is completely filled, which is n equals 0, or when it's not even filled, which is in the gap, all of these three bands are perfectly confident regions where there are sort of no interpretational issues. Yeah.
So are you telling us that the linear, the rat-like band, n equals 0 band is full, but you're not able to resolve the other?
No.
Radically dispersive band.
No, we are. That's happening far higher energies.
But at the same energy, the radically dispersive Landau levels are fuzzed out, which should be called.
No. Here you will see these oscillations. All of these oscillations, let me go back to the previous slide. We can resolve all the Landau levels very precisely and clearly. So these oscillations are bilayer-like Landau levels. Okay, this is the crossing point of the monolayer-like band and the bilayer-like band. So we know exactly which Landau level is coming from which band. So there's no confusion, we can resolve them. In fact, it's super easy to resolve the Landau levels of this guy because the spacing is much larger. Not just that, even at very low fields, we can resolve even the bilayer-like band. So there's no question of resolution. In fact, this experiment is possible because we have the resolution to see the band edge of the monolayer-like band. Is there a question? These are filling factors of the bilayer-like band. So this axis is because we are doing quantum oscillation analysis of the bilayer-like band. So when we measure, we can do a simultaneous quantum Hall measurement to know exactly what the filling factor is. Yeah, so I'm coming to more that dramatically, we do see that in the next slide that I'll show you the effect of it, because simultaneously with this phase measurement, so I kind of explained to you why this sort of pickup in the phase is coming because of the quantum oscillations. There's another part of the data which is simultaneously available, which is the slope, okay, which is gives you the Fermi surface area. And whereas the intercept gives the phase, the slope gives me the area. So I can measure this slope. So if I do it for the bilayer band, I expect that to give me an area which is just the bilayer band, okay? But if you do this, what you see is that the slope will give you the total Fermi surface area of both the bands combined together. And this, both the phase sort of pick up in the quantum oscillation, and this has to happen simultaneously. If one of them doesn't happen, then it doesn't make sense, okay? So we do see that this slope gives the Fermi surface area. We can actually do some detailed measurements of this. So we can do quantum Hall measurements, this is longitudinal, but simultaneously measure GXY. And so we can travel in this sort of valley. Using quantum Hall measurements, we can calculate what the density is. And this is just the sum of the two densities by quantum Hall measurements, not this quantum oscillation measurement. We can do it for the other valley and another valley. So we'll get these. This is just data from simple quantum Hall measurements and how you expect it to vary as a function of magnetic field. And if I now do an independent measurement of the BFT, which is the slope of this line, I get the Fermi surface area, and I plot it without any further conversion. This is just the raw data. This is the black line. It falls right on top, which is the sum of the two Fermi surface area. Okay, so there is this density in force pickup of this additional anomalous phase. On top of it, when I measure the slope of this line, it gives me the total Fermi surface area, not the surface area of individual bands. Okay, and that matches with independent measurement of the quantum Hall extracted Fermi densities of the two bands. So this I kind of already showed you. Since I'm running out of time, I'm going to quickly show you what sort of I promised. So the main takeaway message is that these kind of systems, three-layer graphene or other cousins of multi-layer graphene, are interesting systems because you have some interesting knobs at your disposal to manipulate the Hamiltonian of your system, which is kind of nice. The other interesting story that I kind of, from our point of view, that I told you is the fact that if you have a multi-band system, so measuring Berry phase in a single band system is kind of okay, but most of the interesting non-trivial topological systems have multiple bands. So trying to extract out the Berry's phase, because that's sort of the smoking gun evidence that the band is interesting topologically, is a challenging problem. And one can use another band to extract some interesting information, and that's sort of the main message. Thank you very much for your kind attention.